Grade 9s, we are going to do scientific notation and significant digits today. So this is something that is super, super helpful once you get into high school science, and we're teaching it now because a lot of your teachers, when you get to grade 10, will just assume that you know how to do this, but it's not actually in curriculum anywhere. So everybody just assumes that you've done it at some point, but no one ever actually teaches it to you. So we decided a couple of years ago that we would start doing that, and to give you guys some practice with it, you're going to do what we call the Hohmann transfer, and so that'll happen in the next couple of days, but here's all the information that you need to know before that. So when we talk about regular notation and scientific notation and the difference, regular notation is the standard way that we write our numbers. So as an example, 280 million is written as 280 with 6 more zeros, like that. So that would be 280 million, okay? Scientific notation is a shorthanded way of writing really large numbers or really, really small numbers. So instead of writing 280 million, or think 280 trillion or something even bigger than that with a ton of zeros, we can use scientific notation to shorten how we write it. Okay, so in scientific notation, a number is written as a product of two factors. Okay, so something times something. As an example, 280 million is written as. So I'm going to write it, and then I'll show you what that means. Okay, so 280 million is written as 2.8 times 10 to the 8. Okay, so it's a product of 2.8 and then 10 to the 8 are the two factors here. So we're going to talk about what those two factors are. Okay, so my first factor is going to be a number typically between 1 and 10 that may or may not be a decimal. Okay, so it doesn't always have to be a number between 1 and 10, but generally that's what you're going to see the most of, is a number that is between 1 and 10. Okay, so now for 280 million, that number is 2.8. So it is between 1 and 10, and in this case, it is a decimal. My second factor is always a power of 10. Always. Okay, so it's always times 10 to something. Okay, so the exponent tells you how many places to move the decimal point and then the sign on the exponent tells you the direction to move it. Okay, so that's what your second factor says. Okay, so 10 to the 8, remember from exponents and logs, not exponents and logs, that's grade 12. I was just doing that. Remember from the exponents unit in grade 9 that this is 10 times 10 times 10 times 10, 8 times, right? So this number, if we think about what that is, 10 to the 8, and if I do that in my calculator, just for quickness, 10 to the 8 is, this is 1, 2, 3, so this is 100 million. See, so 1, 2, 3, 4, 5, 6, and then 100 millions. So basically this is 100 million. So that's what this is. And then if we multiply 100 million by 2.8, we get the 280 million. Okay, so then just to verify that, times 2.8, that's our original number. So 280 million. Okay, so that's how scientific notation works. So we're going to talk a little bit more about it. So if the exponent on the second factor is positive, that means the number is very large. Okay, so if we have something like 10 to the 6th, remember that 10 to the 6th, and again, you guys could do this on your calculators or by doing it by hand, 10 to the 6th is going to be 1 million. Okay, 10 to the 9 is going to be, I'll put some commas in there, I should have spaced that better. 10 to the 9 is 1 billion, because if you think about a million, if you multiply by 10, you've got 10 million. By 10 again, you've got 100 million, and then by 10 again, you have a billion. So the difference between 10 to the 6 and 10 to the 9 is 3 more multiplications by 10, and that checks out, okay? So then if you had 2.8 times 10 to the 6th, that would be 2.8 times this, so 2,800,000. Or 2.8 times 10 to the 9 would be 2,800,000,000. Okay, so see how that works. Any number between 1 and 10 multiplied by a large number will result in a large number. Okay, so if you multiply 2.8 times a million, you get 2.8 million. If you have 2.8 groups of a million, you have 2.8 of a million. Okay, 2 millions and then 0.8 of a million. So if you have 2.8 times a billion, you have 2 full billions and then 800 million, so that's 0.8 of a billion. Okay, so any number between 1 and 10 multiplied by that large number, that 10 to the whatever, will also result in a large number. If the exponent on the second factor is negative, that means that the number is very small. Okay, so first we need to understand how we deal with negative exponents. We talked a little bit about this in math, and this is more of a grade 10 math application or math curriculum, but I think we're all capable at this point in the year to understand and wrap our heads around this, and then this is a little bit of a step up for grade 10 math next year. So also this should say first, not first. First, we need to know how to deal with negative exponents. To get rid of a negative exponent, we take the reciprocal of the base and make the exponent positive. So this should be a little bit of a refresher from math. So if you have 3 to the negative 2, if you want to take the reciprocal remembers is the flip. You flip the fraction. So this is actually 3 over 1. We could put that fraction in brackets. So when we do the reciprocal, then we'd get 1/3. And then if we take that negative exponent and make it a positive, we get to the 2. Okay, so that ends up being 1 squared over 3 squared, so we get 1 over 9. Okay, 4 to the negative 5 would be 1 over 4 to the positive 5. There's my reciprocal, there is my new positive exponent. So then that would be 1 to the 5th over 4 to the 5th, and we know 1 to the 5th is just 1, so that ends up being 1 over 4 to the 5th. And I won't simplify that one any further. This one, if we have 1/5 to the negative 2, the reciprocal of 1 over 5 is 5 over 1. So we just write that as 5. So then we could just simplify it like that. Okay, so remember that when we talked about negative exponents in math, negative exponents give us repeated division instead of multiplication. So if you have 3 to the negative 2, instead of 3 times 3, notice how we're dividing by 3 twice. Okay, so 3 to the negative 2 would be 1 over 3 twice. Okay, so you're doing essentially repeated division. So 10 to the negative 2 would be 1 over 10 twice. So that would be 1 over 100. 10 to the negative 3 would be 1 over 1,000. 10 to the negative 4 would be 1 over 10,000. So as that negative exponent gets smaller and smaller and smaller further left on a number line, the number gets smaller and smaller and smaller. Okay, so what is 10 to the negative 3? So that's the same as 1 over 10 to the positive 3. So that's 1 over 1,000, because 10 times 10 times 10 is 1,000. What's 10 to the negative 6? That's 1 over 10 to the 6. And so again, if we look back up, 10 to the 6 was 1 million. So this is 1 over 1 million. So 1/1,000,000th of something. That's a really small number. Okay, so any number between 1 and 10 multiplied by a small number is also going to result in a small number. Okay, so there's the theory behind this first bit of scientific notation. Okay, so to use scientific notation, we move the decimal point in the number to make it shorter. So like 2.8 or 280 million, we moved the decimal point in that number to make the number shorter. So instead of writing 202 and an 8 and a whole bunch of zeros, we just wrote 2.8. Okay, so however, when we do this, it changes the number by a factor of 10 each time. So if you say 28 is 10, oops, that should just be 1, 10 times bigger than 2.8, right? If we move that decimal once, it is 10 times. Or the opposite is also true. If we say 2.8 is 10 times smaller because the decimal's been moved the opposite way, okay? So this is why we must multiply by 10 to the x. We determine the x by how many spots we move the decimal point, okay? So if you're going, so this is for regular notation, changing to scientific notation. Okay, so this is the rule. So if the decimal is moved to the left, the exponent will be positive. If the decimal is moved to the right, the exponent is negative. Okay, so those are the rules, and now we're going to go through some examples, and you guys are going to see this, and hopefully it's going to make more sense as you start to see it. Okay, so if we go from a regular notation of 420,000, so this number isn't that big, but we can use it as a good example. Okay, so what we're going to do, the decimal right here is there, right? 420,000, and then the decimal would follow. Okay, so if we need to move that decimal so that this number is between 1 and 10, we need to move it 1, 2, 3, 4, 5 spots to the left in between after the 4 and before the 2. Okay, so that is 5 places to the left. Now remember, just above this, we said that if we're moving it to the left, the exponent will be positive. Okay, so we're going to multiply 4.2, because that's now what we have. We have 4.20000, right? The zeros don't matter anymore. By 10 to the exponent of, because we went to the left, it's going to be positive, and because we went 5 places, it's going to be 10 to the exponent of 5. So we would write this as 4.2 times 10 to the exponent of 5. Okay, so to kind of summarize this a little bit, 10 to the exponent of 5 is 100,000. If we multiply that by 4.2, we get 4 full sets of 100,000 and then 0.2. So that gives us the 4 full sets of 100,000, and then 20% of 100,000 is the 20,000. So that's how we get that number. Okay, so this next one, we've got 735 million. So again, we want a number between 1 and 10. So we need to move that decimal in between the 7 and the 3. Okay, so then that's 1, 2, 3, 4, 5, 6, 7, 8 spots to the left. Okay, so that means we're going to multiply 7.35 this time because the 5 still is there by 10 to the exponent of 8. It's going to be a positive because it's left, and it's 8 because we moved it 8 places. Okay, so then that's 7.35 times 10 to the 8. Okay, so again, if I do this, if I actually just type 7.35 times 10 to the 8 in my calculator, my calculator is smart enough to do the 10 to the 8 based on BEDMAS first, and then do the 7.35, and so we get that 735 million. Our next one is 0.00897. Okay, so this time we're going to be moving the decimal to the right, which means that we're dealing with a small number, which we are. Okay, so move the decimal after the 8 and before the 9 is where we want it to end up, so that it's between 1 and 10. So that would be 1, 2, 3 places to the right. Okay, so because we're moving to the right, we know that our exponent is going to be a negative. Okay, so now we have an 8.97 times 10 to the exponent of negative 3 because we moved 3 places, and it's negative because we did the right. So this now is 8.97 times 10 to the negative 3. So if we did 10 to the negative 3, that's 0.001. And then if we multiplied that by 8.97, we would get that 0.00897, just like we started with, okay? Or we could do it more like this, where we enter it as one function, but you guys can't do that or you could, it depends on your calculator. Okay, this one, we've got 0.0000014. Okay, so we're gonna move the decimal after the 1 and before the 4. And so that is 1, 2, 3, 4, 5, 6 places. Oops, that's to the right. Okay, so we're going to multiply 1.4 by 10 to the exponent of negative 6. Negative because we went right, 6 because we moved 6 places. It's going to be 1.4 times 10 to the negative 6. Okay, so this is 1 millionth. So we have 1.4 1 millionths. We have a very small number. This one, we've got so we've got 1,712,398,445. Okay, so there's a couple ways that we can look at it. This one has a star for a reason. Okay, so we're going to move the decimal between the 1 and the 7. And so we'd have to move it 1, 2, 3, 4, 5, 6, 7, 8, 9 spots to the left. Okay, so then if we wrote that whole thing as a decimal, it would be 1.712398,745 by 10 to the exponent of 9. 9 because we moved 9 places, and positive because we moved to the left. So that would be 1.712395, 8. That's an 8. 398,745 times 10 to the 9. Did that actually make it any easier? No, we actually had to write more things. Okay, so generally what we would do in a situation like this is we would round to a couple decimal points. So this is 1.7 billion and some, right? So this is 1 billion and then 0.7 of a new billion. So if we rounded that to 1.7 or 1.71 even times 10 to the 9, then that's approximately the same. We've just lost the accuracy of the rest of these numbers, but that's about the same. Okay, so that's how we would generally round those. This one, same deal. We've got a lot of digits after where we're going to have to move the decimal. So we're going to move the decimal after the 4 and before the 1. So that's 1, 2, 3, 4 places to the right. Okay, so then you'd have to do 4.186692 times 10 to the exponent of negative 4. So 4.186692 times 10 to the exponent of negative 4. Again, that's really long. So we can round this. So maybe we do 4.19. We still have to use rounding rules wherever we decide to cap it, times 10 to the negative 4. Okay, so that's approximately the same. We're just losing that accuracy of the rest of those digits. Okay, so in the last two examples, it doesn't actually shorten the number very much unless we round it. Rounding a number changes the accuracy, as I said, and the number of significant digits. Okay, so this lesson was called Scientific Notation and SIGDIGS, which is significant digits. So we'll talk about that next. Okay. Significant digits. Basically, it means that each of the digits in a number are used to express it to the required degree of accuracy, starting with the first non-zero number. Okay, so significant digits are really important in physics. So if you take physics in high school, you're definitely going to need to know this. There's lots of situations where we can apply this. For example, like the speed of light is a really, really, really large number, or the diameter of Earth is a really, really large number. Is it down to a millimeter, the diameter of Earth? Yes, but we use significant digits with a reasonable level of accuracy to round that number and make it something that we can write out using SIGDIGS and scientific notation. Okay, so you guys will see that once you start doing Hohmann's maneuver. Okay, so basically significant digits is counting how many digits there are, and the more digits there are, the more accurate something is going to be. Okay, so basically any non-zero, so any number that's not a zero, is significant. Okay, so 375.9 is 4 SIGDIGS, right? Because each of those numbers is significant, and all of them being there makes that number more accurate. If I said it's about $300, I missed $75.9, right? This is more accurate than like rounding to the nearest 100 or whatever, okay? So any non-zero number is always going to be significant. Zeros are tricky depending on where they are, so here are the rules. If zeros are sandwiched between two non-zero numbers, those are significant. So for example, 1006.9 is 5 significant digits, because all 4 of those numbers count. 1, 2, 3, 4, 5. Okay, and it's sandwiched in between two non-zero numbers. If it's a leading zero, that means it's not significant. Okay, so 0.076 is only 2 SIGDIGS, because these zeros don't actually make it more or less accurate. If you didn't include the zeros, 76 is super not close to 0.076, but without that, the number wouldn't even make any sense. So those don't actually count, just the 7 and the 6 count as significant. Okay, or 00342, we wouldn't write it like that, right? That would just be 342, so this is only 3 SIGDIGS. If it's a trailing zero, so a number at the end, it depends on whether or not it's a decimal, okay? So if a decimal is present, they are significant. So 5.3400 is 5 SIGDIGS. If a decimal is not present, they are not significant. So if it's 53400, so 53,400, this is only 3 SIGDIGS. digs. Okay, so the rules are a little bit confusing sometimes, but you guys don't need to worry too much about this. This is kind of a look ahead at some of high school stuff, but these are the rules. This one makes sense. Like, so if I said an Olympic athlete ran it in 12 seconds, there might be 8 different people who finish in the 12-second range, right? Between 12.0 and 12.999, right? So adding those extra point whatever seconds really increases the accuracy in who's going to win. So that's why those ones are significant. These ones are not, because if you turned this into scientific notation and got rid of those 2 extra zeros, you wouldn't actually be losing any of the accuracy. Okay, so the number of sig digs allowed is based on the lowest number of sig digs that the question presents there. So you can only be as accurate as the least accurate data provided. Okay, so we'll talk more about that in Homans, but something like the diameter of the Earth, that is a significantly rounded number in a textbook or if you Googled it or whatever. So because that's been so rounded, we only can give a number with a rounded answer. So we can't be like, oh, it's 5,463,400, right? Like that's too accurate based on the accuracy of the data provided. Okay, so now that we've learned about sig digs, we're going to complete the last 2 rows again using 3 digits of accuracy. Okay, so that was we move it between the 7 and the 1. We move 9 places to the left, and we're going to multiply 1.71 this time because those are my 3 digits of accuracy. So by 10 to the exponent of 9. This one, same deal. We're moving the decimal after the 4 before the 1. So that's 1, 2, 3, 4 places to the right. So then it's going to be 4.19 if we round that properly, because that 6 would round that 8 up to the exponent times 10 to the exponent of negative 4. So 4.19 times 10 to the exponent of negative 4. Okay. Okay, so now that we've talked about how to go from normal notation into scientific notation, we need to talk about what if we want to move the other direction from scientific to standard. So if we go from scientific to standard notation, this is what we need to do. So my pencil is out of lead. Pencil change. So if the exponent is negative, we're going to move the decimal to the left. Okay, and then we're going to have to add zeros where needed. And I'll show you what I mean by that. If the exponent is positive, we move the decimal to the right. And again, we're going to have to add zeros where that's needed. Okay, so for this, if we think about like if I have 7.24 times 10 to the 6, this times 10 to the 6 with its positive exponent means it's a really big number. So if I want this to be written in standard notation, I need to understand that because my exponent's negative or positive, I want a big number. So I'm going to be moving that decimal to the right. So if it starts here, I'm going to move it after the 2, then after the 4, that's 2 places. So 1, 2, 3, 4, 5, 6. And notice how I drew those little like swoopies like I usually do. And I'm going to have to fill them in with zeros. Okay, so this is equal to 7,240,000. 7.24 times 10 to the 6. Okay, so that's what we mean by adding zeros where necessary. Okay, so we'll go through a few examples of that. Okay, so our scientific notation, so 7.5 times 10 to the 5, so my exponent is positive. So that means I'm moving my decimal to the right. I want a big number. So I'm moving it 5 decimal places because my exponent's a 5. So this means 7, 5. So notice how it starts there. So I'm going to move it 1, 2, 3, 4, 5 spots. And then I just have to fill in a 0 in each of those little swoops. Okay, so each number, each kind of pocket should have a number in it. So this would be 750,000. 3.8 times 10 to the 4, again, my exponent is positive. Okay, so we're going to move it 4 places to the right. So 3, 8, so it goes 1, 2, 3, 4. And so I have 38,000. This one I've got 4.2 times 10 to the negative 3. My exponent is negative, meaning I'm going to move my decimal to the left. So because it's a 3, I'm going to move it 3 places. Because it's negative, I'm going to the left. So for this one, I'm going to write my 4 and my 2 over on the right side of my space, because this time I'm moving to the left. So it's starting between the 4 and the 2. So it moves 1 spot, 2 spot, 3 spots. And then I need to actually put the new decimal and another 0 in front of it. In this one, if I put that decimal there or not, doesn't really matter. But if I don't put that decimal there, that's really, really important. So it's 0.0042. Okay, so this is a very small number. This number is going to be even smaller because my exponent, so 10 to the negative 5 is 1 over 10 to the 5, right? So this is dividing by 10 5 times. Okay, so this is 1/100,000th of a thing. Okay, so my exponent again is negative. I'm going to move it to the left because of that, and it's 5 places because I've got a 5. So again, I'm going to write the 752 over here. Notice that my decimal is between the 7 and the 5, not the 5 and the 2, anything like that. So 1, 2, 3, 4, 5. That's where my decimal is going to go. I'm going to fill a 0 in and put a 0 in front. Okay, so that's a very small number. Okay, so for practice, you guys need to practice going from regular notation into scientific notation, and then from scientific notation into regular notation. For this one, we're going to just use 3 significant digits. So that means basically you can round and get rid of that 0.97 here. But I think the rest, we're just going to go with however many digits you think is appropriate. So the rest of them, it's like 2, 3, maybe 4. For this one, just use 3. Okay. And then all of these ones should be a-okay. Okay, so this is your practice. There is an answer key posted to this, but you should attempt first, then check. Okay, so don't just copy the answers off the answer key that's posted on this on Genius. So attempt this by yourself, then check your answers to make sure that you've done it right. Okay, so there's a PDF of this whole document on Genius, and so you can scroll to the bottom and check your answers. Okay, this part's not going to be for marks, but the more comfortable you feel with this, the better off you're going to do once we get into the home and maneuver tomorrow. So if anything doesn't make sense, you are free to send one of the teachers an email. You can also go back and rewatch this as many times as you need to, but we are happy to help if that's needed. Okay, so let us know if there's any problems, but hopefully all of this made sense and you are now pros at scientific notation. Okay,